Bismillahirrahmanirrahim. For the next 3 lectures, we are going to be covering the normal distribution, and I am going to be doing some real mathematics. In my youth, I was a mathematician. I did my bachelor's in maths, and I thought it was all important. And I used to teach it. So basically, the material in these 3 courses, these 3 lectures will be something which might take a whole course. And now I am just going to rush over it rapidly because basically, you see, in mathematics, one thing is to know how to do something. For example, when you add 2 fractions, you can know how to do it by saying, okay, we multiply together the denominators and we multiply the top of one by the bottom of the other, and then we just add. Okay. But what does it mean? You may not have any idea. Why does this work? You may not have any idea. And how to use it? You may not have any idea. So, for a long time I have been focusing on, instead of learning the mathematics, learning what the mathematics means and how it is used, and that's mostly been my focus. And actually, and in this course also, and for a long time I have stopped teaching proofs and equations and formulas. I've just started working on meaning and use. But this class is a class in econometrics for econometrics students. Actually, if it was PhD econs, I would not be teaching this material but for econometricians, you have to know something about the mathematics and the background. This is like going into the engine of the car. To learn how to drive, you don't need to know what is in the engine. But for the next 3 lectures, I am going to be teaching you something about the engine because first of all, it gives you some confidence. You are using something but you don't know what it is. You say, okay, here is the formula, and some student asks you, well, how do you get it? Well, you say that, oh, because my teacher said so. So this is not so good for an econometrician. For someone who is a user, the computer says so is good enough. This is the answer the computer gave me. How it got it, you don't know, you don't care. But for an econometrician, you have to know how the computer got this answer and be able to actually replicate. So we are going to do some heavy math. But even then, I'm not going to focus on proofs. And actually, what I'm going to do is to cover the highlights, the very, very critical points. And that, if you read the book, it will be a whole chapter and there will be one formula in it which is the crucial one. But you will not know, okay, this is the crucial one and the 10 other things are not so important. So I am going to give you some very concentrated dose of very heavy mathematics in very short pieces, and just focus on the crucial things. And there is a lot of background. And I have actually on the website I have put the links to the proofs, the details. There's lots of this material is very well known. Unlike most of the material that I have been covering, this material on normal distribution. Normal is the backbone of statistics and probability, and everything is known about it. And there are 1,000 ways and there are 1,000 books. So this material is known. I have given some links to some resources which provide a good exposition of the material that you need. So even now from this lecture you will not be learning the proofs and the formulas, but you will learn something you will learn the highlights, and then you can, at your own pace, you should work on acquiring those skills. I mean, the formulas that I teach, learn the proofs. The proofs are available, and learn how to go and get comfortable with how to derive those things. By the way, the homework assignments, I would like for you to arrange a class. Now, several people have solved it, and I would like you to go through and make sure that everybody understands those things, because there is lots of extensions that I don't have time to cover. If I started to cover all the details, we would never finish this course, and you will not get to the heart of the matter. So, but there are also learning is by doing. Unless you, no matter how much I talk, you will not learn unless you work on it yourself. So, أعوذ بالله من الشيطان الرجيم بسم الله الرحمن الرحيم.
ومن الناس والدواب والأنعام مختلف ألوانه كذلك إنما يخشى الله من عباده العلماء إن الله عزيز غفور.
So the fear of Allah is the root of all wisdom. Allah Ta'ala has created many things in the realm of the real which we can see and in the realm which we cannot see. So there are things which exist in the worlds which Allah Ta'ala has created which we cannot see. This has been given the name in English of the Platonic world of ideals, and in our religious traditions it's called the Alamul Mithal, the world of the imagination. Well, that's not quite the right translation. Anyway, this normal distribution is one of these things which exists in the world of the imagination. It doesn't exist in the real world. There is no normal distribution in the real world. But this has a very beautiful theory, and just like the Euclidean geometry, it's a very beautiful theory. It's about lines which go from minus infinity to infinity, plus infinity, and they are perfect. There is no such thing in the real world. You cannot find a line which goes from minus infinity to plus infinity. But this is something which exists in this imaginary world. There are many constructs in the imaginary world which it is useful to learn about. And so this is one of them. So this is the first definition. A normal distribution density is defined like this. This is the function f1 over square root of 2 pi times sigma. Another way to write this is to write the square root of 2, square root extends over the sigma, and then you put sigma squared. So it's 2 pi sigma squared and under root. So both of these things are the same thing because sigma is always positive. The variance is always a positive number. If it was negative, then there would be a problem. And then you have this thing in the exponent. Now, what are the properties of this density? Well, this is the shape of the density for different kinds of mu and sigma. Mu is a translation parameter, and sigma is the shape parameter. So, sigma, by changing mu, all that happens is that we shift the density from one place to another place. So this is very easy to do in Excel. So what I did was I just wanted to make a graph of the normal density. So here's my x, which goes from minus 10. I created this grid of x values. Then I created this norm dist. Norm dist with I want the mean 0 and 1. So C1 and D1, these are entered into this formula. Norm dist of A2, that's x. And then the mean is in C1, which is 0. And the variance is in D1, which is 1. And then the 0 at the end tells you that this is going to be a density and not the cumulative. So now all of these numbers, they are the f of x. And then I just ask Excel to graph it. And here's the graph. You can see the graph here. And this is like your normal density. And now I wanted to look at another density to show how this works. So here's another density with about the same formula, except that it's using E1 and F1 as the parameters. So now I have here in the second chart. So in the second chart, what we have done is, okay, so the orange line is the 0, 1, which is the standard normal density. Very important to understand. The standard normal density is very basic. So today's lecture we are going to cover the univariate one variable density. Next lecture will be bivariate, and the third lecture will be multivariate. After that we'll come back to the real course. So now, as you shift the mu, see 0, 1 and is compared to 1, 1. So the blue line is I think the standard normal, and the orange line is the shifted. It has mean 1. So the whole density has been shifted by 1 unit. Now if I change this mean to 2, what will happen? It will shift. You see, it shifted a little more, and if I shift it to 4, it will shift a little more. So that's all. This is the shift parameter. Now suppose I go back to make this 1, and now I want to experiment with what happens when we change the variance. So as the variance increases, it will become, hey, ye kya ho gaya? Acha, I put it 1, 0 nahi kiya. 0. Enter. Okay, so now both of them are coinciding, one on top of the other. Now if I increase the variance, what will happen? It will spread out, yes. So let's put the variance at 4. You see, it becomes very spread out. If I put the variance at 2, it becomes sharper. Now suppose I put it at 0.5. See, now it becomes sharper, and as I move it towards 0, it will start to become fully concentrated. There is the famous delta function in mathematics, which has mass 1 at 0, at 1 point, and that is what it converges to. So all of the mass is becoming concentrated at a single point. So this is what the density looks like, and so here you can see that the first three densities are just changing the variance, and the third density is shifting the. Alright, now one more thing that is very important to learn about the normal distribution is the probabilities of 1, 2, 3, 4, 5 and 6 standard deviations. You don't need to know all of them, just 1, 2 and 3. So the probability that x is between minus 1 and plus 1, that's probability of x being within one standard deviation of its mean, is 68.3%. The 0.3 doesn't matter, 68% is good enough. Similarly, between two SDs, there's 95% probability. Between plus or minus 3 SDs, there is 99.7. Also, you can remember that between plus or minus 2.6 is 99%. The normal distribution is so central that these numbers should be memorized, because there are many times that you can make calculations of probabilities just without any paper and pencil if you know these numbers. So this is part of experience as a statistician. Now numbers get very bad as soon as you go up. So x greater than 4 SD is 7 e to the minus 5, which is less than 1 in 10,000. 5 SDs you are at 1 in million, and 6 SDs you are in 1 in trillion. So there is something well known called in business they call it Six Sigma quality control, which means that basically your probability of defects should be 1 in a trillion. Now these numbers have meaning. If you are talking about something like 1 in 10,000, 4 SDs, that means that if you run a simulation of a normal variable and you run 5,000 trials, 6,000, which is what we are often doing, in your, like we do 1,000 trials to get the p-values in our simulations, or we can do 2,000 or 4,000, you will never see a random variable of normal which is at 4. So normal variable does not have outliers. This is a very important property to understand. At 5, it's 1 in a million. So if you run 50,000 or 100,000 simulations, you will never see a value of 5. Conversely, so if you're running a random variable which is supposed to be standard normal under the null hypothesis, and you see a 5, you can reject the null hypothesis that this is a normal. It can't be a normal. And 6, that's just impossible. So these are very, very low p-values for a normal variable. This is something that one should know, because Again, this is practical experience with normal variables, which is usually people don't have. Alright, just want to generate some normal variables to show you. Yes, there's an experiment. कहाँ पे है ये? Data analysis, random number generation. I want to generate two variables, 100 normal. Okay, so there's our 200 normal variables. You will see that these numbers don't change very much. I mean, don't fluctuate very much. Let's look at this. Equals max. So you see, I'm trying to teach you hands-on understanding of normal variables, not theoretical understanding, which is actually what these lectures are about. So this 2.8 is the largest number, and if you remember, 99.7% is going up to 3, so this is about what we expect. I mean, in sorry, that's too much. 99% is at 2.6. So in 100 trials, we should see about 2.6 as the maximum, and that's what we are getting. Let's look at what happens to the other column. 2.19, so this is much smaller than 2.6. Again, so you can get an idea. Now, one thing that to understand is that everything has a distribution, and this distribution is important to know. So, for example, I want to find out what is the distribution of the max of 100 normal variables. This is no longer going to be normal. And now, by simulation, I created one, and I created another one, and if I create a lot of them, I will get a random sample of maxima of normals. And so I can study what does the maximum of 100 normal numbers look like. And I can take a sample of 100 of those by creating thousands, and then I can create a density function for those to understand what the density function is. I can calculate the mean, the variance, everything I want to know about the maximum of 100 normal random variables. And just like that, for any kind of random variable, no matter how complicated it is, and this would be difficult to study by analytical methods, by the formulas, by the methods which we are going to study now, but it's easy to study by simulations. Now, what I wanted to show you here was something about how this normal is not, the fact that the normal is very stable is not something that is true of all random variables. It's a very specific, special property of the normal. So what I'm going to do is I'm going to show you what happens when you take the ratio of two normals. It's a very simple variable. I take A1 and I divide by B1, and I've got a ratio. It's 2.23, no problem about that. Let's see what happens. You see, unlike the normal, you have 0.23, 19, 69, and then 9.32. Yes, this is a Cauchy distribution. One of the things of the Cauchy distribution is that it has no expected value. The expected value is actually plus infinity minus infinity, so it can be anywhere, and it shows up in the numbers because the numbers become wild. You see, unlike the first case where you see, if you look at the first three numbers and you say, okay, well, I'm going to predict what the next number is going to be, you're not going to run into serious troubles. You can say, okay, I have seen three numbers, and so they range from minus 1.2 to 1.7, so the next one will also be within this range. Your experience counts. Here, if you look at 0.3, 0.23, 0.19, 0.69, there is no way you're going to say that the next number can be 9. This is going outside of experience. This is called the black swan phenomena. All your experience is that all the swans that you see are white, and then suddenly you see a black swan. It's outside the range of your experience. So just like this Cauchy distribution has a tendency to generate variables that, okay, so we have 9 max, then most of the numbers are coming out very nice and reasonable, 2, 3, minus 1, 5, 9. Oh, minus 22. You see? Again, this is going outside the range of your experience. The whole range, this is going from minus 3 to plus 9. 22 is nowhere within the realm of possibility. You would never think that the next number could be 22. So this is the kind of thing that can happen in very easily in the real world. And so the whole this Nicholas Nassim Taleb has been doing a lot of work on this, the black swan phenomena. He says that most of the models that we are using are junk because they are based on this assumption that black swans will not occur, that our experience counts. But the world is in many situations places where the experience doesn't count. The experience is actually misleading, like the global financial crisis. Things happened which were totally unrelated to the past. No model could predict that. So if you want to study a world in which there are black swans, you have to use different techniques. And the normal distribution is exactly the opposite of the black swan. And the normal situation holds control over the real world in the sense that it's fixed in the minds. There were famous financial hedge fund. Anyway, 2 Nobel Prize winners in finance started this hedge fund, and they used the theory to how genius failed. They used this theory to calculate the optimal strategies for the fund, and they made a lot of money for 2 or 3 years, much more than everybody else, and so everybody thought this was great. But then they had a massive collapse. They not only collapsed the whole fund, but they collapsed the whole economy almost. The Federal Reserve had to go in and bail out the economy. Because, and when somebody asked the authors, what happened, you were doing all these formulas, they said, well, a 6 sigma event happened, something which, exactly, which has a probability of 1 in a trillion. It couldn't happen according to their theory, but the real world didn't follow their theory, that's all. The real world, they were assuming normality for some things, and these were not normal distributions. So that's the thing that is important to understand. Okay. Now, we come to the mathematics. So, the expected value of any random variable is defined. We've already defined it in the discrete case. Now, in the continuous case, it's the integral of x times f of x dx. And we can calculate for the normal density, which we have already defined, that this is going to equal mu. And I will show a little bit about how this can be done. Then the expected value of x squared is the integral of x squared f of x dx. These actually, both of these integrals can be done analytically. Unlike the integral of f of x dx, you cannot calculate that by any easy method. There is a difficult method which is used, and I have given a link to YouTube demonstration which shows how you do it. Basically, you cannot do it directly because f of x is not analytically integrable. There is no function which you can differentiate which will give you f of x. And basically, if you don't have that, then you cannot get an analytical solution. But there are some mathematical tricks you can use to get the whole integral from minus infinity to plus infinity. You cannot get the partial integral from a to b. If you could get that, then there would be no need of tables. But actually, everywhere you see the normal is tabulated. It's not. You don't see any formula for it because there is no formula for it. But integral x f x, that you can integrate. You can integrate exactly because there's a integration by parts you can do. X dx is the derivative of the part that you can make, and so similarly x squared you have to do 2 integrations by parts and you can get the answer. And so the first integration gives you mu and the second gives you sigma squared plus rho squared, mu squared. This is called the second moment. It is also called the second raw moment to differentiate it from the second central moment, which is another important concept that we will introduce. Basically, when you take when you subtract the mean from a variable, that's called centering. So if x has mean mu, then x minus mu is the centered variable, and the mean of the centered variable is 0. So the moments of the centered variable are the central moments, and the moment of the original uncentered variable are the raw moments. So the variance of x is the second moment of the centered variable x. So x is equal to expected value of x minus mu squared, and that is equal to this kind of calculation is something that you need to learn how to do. When you have x minus mu squared, you can expand it by the standard method. It's x squared minus 2x mu plus mu squared, and then expectation is linear, so you can split it up. So it's expected value of x squared minus 2 times expected value of x times mu. Now the mu is a constant, so it can be taken out. Ex is also mu, so it becomes mu squared. So this is minus 2 mu squared plus mu squared, and that becomes ex squared minus mu squared. And I just showed in the previous slide that ex squared, the second raw moment, is mu squared plus sigma squared. So the mu squared subtracts from the mu squared, cancels, and you get sigma squared left, which is the variance of the normal. And the standard error of x is called the square root of the variance by definition, and that's just sigma. Now, one very important thing to understand here is that these are all pre-experimental numbers. That means we are talking about the imaginary x, which has all possible outcomes, and the outcomes have probabilities, and there is nothing, these are not things which are happening. Now, post-experimentally, x takes a particular value, and so if you take a sequence of observations on x, then you take the average of those observations. The average of those observations will have some match to the expected value. The expected value is the pre-experimental concept, and the average of the observations is the post-experimental concept. Similarly, the standard deviation is a post-experimental concept. You take the observations and then you take the list of numbers and you calculate the standard deviation. The standard deviation is matched to the theoretical pre-experimental standard error. They will be similar to each other. The law of large numbers that we will study later in this lecture shows that if n goes to infinity, the sample size goes to infinity, the sample standard deviation will converge to the theoretical standard error. And similarly, the sample average will converge to the theoretical expectation, which is also called the population mean if you are taking the random variable as a random sample from a population. Okay, so these are some critical theoretical mathematical concepts, and here I have skipped the derivations, but these are derivations that you should learn as econometricians, and these are available in the notes. Now, the most important concept for dealing with the normal is the moment generating function. So, first of all, this is expected value of e to the theta x, but to understand why this is important, you have to expand the e to the theta x in its Taylor series. And so if you look at e to the theta x, it's 1 plus theta x plus theta squared x squared over 2 factorial plus theta cubed x cubed over 3 factorial, and so on. So now when you take the expected value of this, now there are some very fancy formal mathematical issues involved here. This is an absolutely convergent series. What that means is that for most random variables, what that means is that there's no the tail end terms become very, very small. So if you take an approximation by taking a few terms of this, you get a good approximation, as opposed to series which are badly behaved and the tail terms become very bad. So if you ignore them, you get into trouble. But this is a very well behaved series, and so if you just take a few terms, you get a good idea of what the whole series is doing, because the bigger terms are very small, so they don't affect things. Even the sum of all of those tail terms is very small, so they don't affect things. So One of the important things to note here is that when you take the expected value, and expected value is linear, so you get 1 plus theta times the expected value of x, plus theta squared over 2 factorial times the expected value of x squared, and so on. So all of the moments are sitting in this function. And that's exactly why it's called a moment generating function, because all of the moments are embedded into this function. And you can get them out. That's the beautiful thing. Because what happens is, if you look at this formula, the way you get them out is you differentiate. Suppose I differentiate this with respect to theta, then what will happen? The 1 will disappear. The t will drop out. T times e of x will be just ex. And all the other terms will have a t in it. The t squared will become t, the t cubed will become 3t squared, and so on. So if I differentiate once and set t equal to 0, I will get out exactly ex. Now, this process can be continued because the t squared, you see, the 2 factorial is matching everything which is coming down. When you take the t squared, the 2 comes down, cancels with the t squared, and you get t times ex squared. So the second time you differentiate, the ex squared will be there, the ex will disappear because it's a constant, and when you set t equals to, all the higher order terms will disappear. So it's a very simple thing. You take the MGF, differentiate it once, set theta equal to 0, and you get ex. Differentiate it twice, set theta equal to 0, you get ex squared. Whichever power you want, ex to the k, differentiate it k times, and set theta equal to 0, you get ex to the k. So this is the very nice and pretty and elegant thing about the MGF. And this is not the only thing. The MGF has also many other wonderful properties. That's why it belongs to the Platonic world where everything is perfect. So here, the MGF of the normal can be computed fairly easily. I have a short set of notes in which is attached to the website, in which there is a 2-page calculation. It's very simple and very nice and elegant calculation. And when I was young, I would have gone through this calculation in this class and explained it all. But now I leave it to you to go through it and check how this is done. It's basically an integration exercise. Actually, the pretty thing about this is that you don't actually have to do any integration, because you start out by knowing that the integral of f of x is equal to 1. So then when you add the e to the theta x, then you can rearrange this term. You just play with the algebra and you rearrange. So you have an integral which is integral e to the theta x f of x dx. Now the e to the theta x comes into this exponent, and you can rearrange this term so that it looks like the integral of a normal density times something which doesn't involve x. So when you get the integral of the normal density, that's automatically 1. And the part that doesn't involve x, that's the moment generating function. And that part that doesn't involve x is exactly what's written on the second line. So this comes out after a lot of algebra. It's a very elegant calculation because you don't actually have to do any integration. You just have to arrange things into a density function and then recognize that the integral is 1. So it's done in that set of notes. But if you understand what the trick is, you will be able to follow the calculation easily. There is a trick to integration which is not a standard trick. I mean, this is not one that is taught to you in the calculus textbooks. It's a special trick in probability, and it's used quite often when you are doing integrals in probability theory. You just try to change things into density functions, then you say that, okay, I know this integral already, so I don't actually have to do any real integration. So anyway, here's the x e to the theta x, and I've already explained this point that the moments occur in the expansion of MGF, and so there is a technique to get the moments out from the density function. If you want ex to the k, you differentiate the moment generating function k times and set theta equal to 0. And now here is the moment generating function, and we can do that. So first time you differentiate, what will happen? E to the x, you have to differentiate what's in the inside the exponent. So what will happen? What's the derivative of what's inside the curly braces? Yes, yes, all of you are mathematicians. Yes, yes. The exponent is just going to reappear again, and then you're going to have the derivative of what's inside the exponent. What's that derivative? नहीं अभी theta 0 नहीं कर रहे हैं, just the derivative. What's the derivative? E to the something, the derivative is e to the something again times the derivative of the something. So what is the derivative of the something? It's mu plus sigma squared times theta, right? Now, when you set theta equal to 0, e to the whatever becomes 1. Because theta is 0, e to the 0 is 1. Sigma squared theta disappears and all you're left with is mu. So we have proven that the integral of x, f of x dx is equal to mu. That is what I claimed, that the mean is mu, and now the MGF is one way to prove it. The other way to prove it is direct integration, and you should also know that method. But okay, so the non-central moments, these are the raw moments. The first moment is just mu. It's wrongly written as m over here. I don't know how that came about. Anyway, I just copied it from Wikipedia actually. The second moment is mu squared plus sigma squared. Again, you see, you start with now you have a complication. This is not easy. You have e to the something times mu plus sigma squared theta. And now when you differentiate it, you will get u dv plus v du. So you get e times the derivative, which will be sigma squared. Theta will disappear. And so the sigma squared will be one term. The other term will be the mu plus sigma squared theta times the derivative of e to the something. And so that will get mu plus sigma squared theta times itself again and times e to the something. So that will give you the mu squared term after you set theta equal to 0. And as you go on, this will become more and more complicated. First you have one term, then you have two terms, then you have four terms, then you have 8 terms, and so on. But it's all routine. And so these are the numbers that you come out. Now, from the non-central moments, you can get to the central moments. And that's what I would like to show you. So how do you calculate the central moments from the raw moments? I already showed you how to calculate the variance of x by taking the quadratic and expanding it and then calculating. So I'll show you how to do the third power, and that will show you how to do the general case also. So I want to calculate expected value of x minus mu cubed. I can get the raw moments by differentiating the moment generating function, even though it's a bit painful, and you have to be very careful to keep track of the numbers, otherwise you make mistakes. But it's a routine calculation. And nowadays there are programs like Maple, Mathematica, which will actually do the symbolic differentiation. So you feed them the function and it will produce the derivative of that function. So you can do it without errors. Okay, now, so I can get the list, I can get all the raw moments. Now how can I calculate the central moments? Well, the central moments, actually, this is one way. This is just to show you the manipulation. The other way is to set mu equal to 0 in the central moments. When mu is 0, then you automatically get central moments. But I want you to learn this one also, because this kind of calculation is needed in some places. So expected value of x minus mu cubed, this is the third central moment. So what we do is we expand x minus mu cubed, so it will become x cubed minus 3x squared mu plus 3x mu squared minus mu cubed. Okay, so we write that as the expectation. And now we break up the four terms. So the first one is ex cubed. So ex cubed, now we can go back to our table of raw moments and write down what that is. And that turns out to be mu cubed plus 3 mu sigma squared. Then we have 3 mu ex squared. So now I substitute for the second raw moment, mu squared plus sigma squared. So I have 3 mu times mu squared plus sigma squared. Then I have the third term, which is 3x times mu squared. I take the expected value of x, that's just mu, so that becomes 3 mu cubed. And then I have minus mu cubed, which doesn't require any calculation. So after you look at all of these terms and you arrange them, you find that everything cancels and you get 0, which is not surprising because all the odd moments of x are 0. And we can also confirm that from the table. If I look at the third moment and I set mu equal to 0, I will just get 0. And the same is true for all the odd moments. So that's how you calculate the moments. Now, some very important properties of the normal distribution. The crucial property is that the linear transforms of normals are normals. If x is normal with mean mu and variance sigma squared, and y is equal to ax plus b, then y is normal. So once you know that y is normal, then you can calculate the parameters that it must have. Because a normal is characterized by 2 parameters, the mean and the variance. And if I know that y equals ax plus b, that's enough to allow me to calculate the mean and the variance of y. So the mean of y, Ey, is just equal to a times ex plus b, and ex is mu. So the mean of y must be a mu plus b. So the normal distribution of y must have the mean a mu plus b. The next thing is to calculate the variance. Now the variance of y equals the variance of ax plus b. Now adding or subtracting a constant doesn't cause any change in the variance, so the b will drop out of the calculation. The variance of ax is a squared times the variance of x. That's a very important formula that you must know. And now the variance of x is known, it's sigma squared, so it's a squared sigma squared. So it follows that the y is a normal distribution with mean a mu plus b and variance a squared times sigma squared. Okay? Now, this has 2 implications, very important. One is standardization. If I start with any x, I can get to the standard normal density by subtracting the mean and dividing by sigma. So if I take x minus mu divided by sigma, then z must be normal. I just apply the formula. If I take a mu plus b, you see this is a special case of the formula. So I am subtracting, I'm taking 1 over sigma times x minus mu over sigma. So 1 over sigma times x means that I have mu over sigma minus mu over sigma. That will convert to 0. So the mean will become 0. And the variance will be 1 over sigma squared times sigma squared. So the variance will become 1. So this is standardization. For any variable, actually this is not just for normal variables. If I take any variable, I subtract the mean and divide by the standard error. That's called the standardization of x. And the standardization of x always has mean 0 and variance 1. By definition, that's what it means to standardize. There's another thing. There's centering. Centering any variable means to subtract the mean from it. That will always have mean 0. And there's also scaling. Scaling means to divide by the standard error. And that will always have standard error 1, even though it may not have center 0. So if you do both centering and scaling, then you get mean 0 and variance 1. So basically you can go from any variable to a standard normal by subtracting the mean and dividing by sigma. And conversely, if you start with a normal 0, 1, you can generate any normal variable by taking mu plus sigma z. Z is the standard symbol for normal 0, 1, standard normal. So if you multiply by sigma, the variance will become sigma squared, because when you multiply by a constant, the variance gets multiplied by the square. And when you, but the mean will be 0. When you add mu, it will become mu. So this is very important to be able to move back and forth from standard normal to general normal, and this is used routinely because we use the standard normal tables to calculate normal probabilities for any normal, and that's done by this method that you start with a normal, any normal, and you standardize it, then you compute the probabilities for the standardized version of the variable. Now we come to the most important part, which is the most difficult part also, that basically all random variables converge to normals. This is the central limit theorem. Actually, there are two theorems, one that I want to cover. One is the law of large numbers, which says that if you take the average of any sequence of variables, it will converge to the mean of one of them. This is true for identically distributed variables, if all of them have the same mean. The same theorem works if all of them have different means, but then you have to do it slightly differently. The way that you do it is that first you must center the variables. So if you have 1 over n summation I equals 1 to n xi, then you replace that by 1 over n summation I equals 1 to n xi minus mu I, where mu I is the mean. Now this set of variables, everything has mean 0, so this is going to converge by the law of large numbers to 0. Now once you have this, then you have that 1 over n summation xi minus 1 over n summation mu I is converging to 0, so that the limit of these random variables, the average of the random variables, is the same as the limit of the constant means of those random variables. So now you can, even if those constant means don't converge, you can approximate the random average by a fixed number, and that's very important to be able to do. So because the random numbers are fluctuating, but the constant means are not. So in large samples, the average of any random variables will be close to the average of the means. The average of the means is a constant. So if you want to approximate the average of random variables in large samples, you can do so by one number, which is the average of the means. That's the meaning of the law of large numbers. Now, similarly, you can also approximate the distribution of the sum of numbers by a normal distribution if you do it correctly, and that's and both of these come out of a very simple, well, not simple, it's very complicated, but the key to this is using the cumulant generating function, the key to understanding how this works. And so I'm going to try to show you how this works, and this is only a sketch, but the real proof is not all that difficult. I mean, as econometricians, you shouldn't be scared of the real proofs. So what happens is that if you take the sum of n random variables, I'm calling this S of n, this is the first line in the slide, so it's summation I equals 1 to n xi. Now the key to understanding asymptotics is again the moment generating function. Expected value of the moment generating function of the sum is the expected value of the exponent of theta times S of n, and the exponent of the sum is the product of the exponents. And now a crucial assumption here is independence. If the random variables are independent, then the expected value of a product of random variables is the product of the expected values. So you can write this as the product of the expected value of x theta xi. What this says is that the moment generating function of the sum is the product of the moment generating function of the individual variables. That's a very convenient result, and that's what allows you to do asymptotics. And most of the derivations that you see will be based on the moment generating function. But that's very clumsy and awkward and makes the proof very non-transparent. So if you look at any proof in the conventional books, you will not find it very illuminating. It is just a sequence of steps one after the other, which doesn't lead to much insight as to what's happening. So what really makes things nice and easy, if you just take one more step, instead of the MGF, you move to the CGF. The CGF is called the cumulant generating function, and it's just the log of the MGF. But the point of taking the log is that when you take the log of the product, it becomes the sum of the log of the MGFs. So the original thing was a sum, and now the cumulant generating function is also the sum. And what is its sum? It's a very nice sum. It's the log of the expected value of x theta x. So there are two operations. First you take the exponent of theta x, then you take the expected value, and then you take the log to undo the effect of taking the exponent. So so basically there are so the cumulant generating function of the sum of random variables is the sum of the cumulant generating function. This is what makes things nice and easy. The other important property of the CGF, first of all, what are cumulants? So just like we can expand the Taylor series of e to the theta x as 1 plus theta squared over 2 factorial times x and so on, which we have just done. So you can write the Taylor series of k theta x, which is the log of that. And that will be, now this one doesn't have a constant term, because at theta equals 0, this has to be 0. Because at theta equals 0, e to the MGF is always 1. Because e to the theta x is just, at theta equals 0 is just 1. Expected value of 1 is 1. So when you take the log of 1, that's going to be 0. So at theta equals 0, this is 0. So there is no constant term in the expansion of the cumulant generating function. So then it's theta times something. Whatever that something is, we call it kappa 1, and that's the first cumulant. And it turns out that this is just x. You can just work it from the MGF. Now the second term is theta squared 2 times kappa 2. It turns out that kappa 2 is the variance. And similarly, you go to theta 3 over 3 cubed kappa 3. This is the third cumulant, and so on. These higher order cumulants have complicated expressions in terms of the moments of x. But there is something very nice which we'll show soon. Okay, so you get the cumulants out of the cumulant generating function exactly like you get the moments out of the moment generating function. You differentiate and set theta equal to 0, you get the first cumulant. You differentiate twice, set theta equal to 0, you get the second cumulant, and so on. But the important thing is that if you take the first important thing is that the CGF of the sum is the sum of the CGFs. That's almost obvious. And the other important thing is that suppose I have k of theta summation ai xi, then the summation can be taken out because and the ai also behave in a very interesting way. When they are multiplying xi, instead of multiplying xi, you can take them to multiply the theta, because basically you're taking x of theta x. So if a is multiplying x, you can also make it multiply theta. So it's the same thing. So now the cumulants have a very interesting property that if you take kappa 1 of ax, that's a times the expected value of x. If you take kappa 2 of ax, it's a squared times the kappa 2. Remember, the variance is multiplied by the square. The third cumulant is multiplied by the cube. The fourth cumulant is multiplied by the fourth power, and so on. Let's see. How does one establish that? There's some simple way which I'll let you think about. It's not difficult. All right. So now, once we have this cumulant generating function in hand, you see, I'm just giving you a guided tour that highlights all the path that the mathematical work I have left for you to do on your own. Or if you don't do it, you can still guzara hai, you can still learn how to drive the car. But for an econometrician, I mean, as long as you know these results, you will know what's happening. But if you can derive them, and it's not difficult, that's what I want to say, that it's not a very hard calculation, but so I'll suggest that you have a session with Ahsan Satti so that you can go through these proofs in detail. I would like, because econometricians should know. I mean, they'll be cheating otherwise. If this was a PhD economics, it would be all right. They don't need to know the proofs. But for PhD econometrics, you should know these proofs. And if they can do it in Punjab, you can do it in Islamabad also. The other session that I would like you to arrange is that for yourself go over all of those exercises. Make sure that everybody knows how to do those exercises. So आमने इनके साथ arrange कर लेना. Now, I want to study the asymptotic behavior of the S of n, and it's so beautiful. It's really Platonic world of perfection. So, what we do is, first of all, we have to center things. S of n minus ESN, and now I'm thinking about the simplest case where all of these variables have the same distribution. All of these theorems extend to this is called the IID case, the independent identically distributed case. The other case is the INID case, the independent not identically distributed case. Now, both of these cases are quite similar, not much change in them. If you have an INID case, what you do is you replace the x by the standardized variable. So xi minus mu I divided by sigma I. Then now, even though these are not identically distributed, all the theory goes through, because actually you don't need identical distribution. You need that all of them have the same mean, 0, and the same variance. So once you standardize, you get all of them to have the same mean, 0, and the same variance, and that's all you need for the proof. And so you get your asymptotic result for this, and then from this you can get the result for the random variables. You can separate out the summation mu I over sigma I, and so you get a result for the original variables on the basis of the standardization. So it's not difficult, but the IID case is simpler. So I'll do that just to show you how it works. So now, what happens to the variance of Sn? So first we standardize. So we center. So we get rid of the means. Everything has mean 0. So now the variance of S of n is the sum of n terms, and we just the variance of the sum is the sum of the variance. So the variance is n times sigma squared. So the variance goes to infinity. The sum will not converge to anything nice because the variance keeps increasing. So now we look at variance of S of n divided by n. This is the average value of the random variables. So what will happen? Well, 1 over n will come out with n squared. The variance itself is n sigma squared. So when we divide by n squared, the variance will go to 0. Now, there is one very simple result. There is only one variable which has variance 0. Because you see, variance 0 is the integral x squared times f of x. We are thinking of a variable with 0 mean now. So now, if x squared has any chance of being anything different from 0, the variance is going to be non-zero. It's going to be positive. The only thing that has variance 0 is something which has 100% probability of being equal to 0, and nothing else. So basically, if the variance of this S of n over n is going to 0, that means Sn over n equals 0 with probability 1 in large samples. And that's exactly what the law of large numbers is, that the probability that S of n over n is within plus or minus epsilon is going to 1 for any epsilon. That's proven by the Chebyshev inequality, but also it can be proven by this moment generating function method. So, if we leave S of n alone, it diverges. It becomes, the variance goes to infinity. If we divide it by n, it converges to 0. Now, there is one exact rate at which it will neither diverge nor converge. It will remain random. And that is square root of n. If I take S of n, divide by the square root of n, then on the numerator I have n sigma squared. In the denominator, the square root of n squares to become n cancels, and I have sigma squared. The variance converges to sigma squared. This is going to be a stable random variable. The variance is not going to infinity, it's not going to 0. And this is the only scaling which will do that. And so now what happens, and this is the central limit theorem, beautiful, magical. which we will show, that every sum eventually becomes normal. So it will be normal with mean 0 and variance sigma squared. And this is regardless of what these individual variables are. You can put anything in there in the sum you like, and ultimately, as long as they are all random, the sum will come out to be normal. And that's why the normal has a very important role in the statistical calculations. So, now it all comes out from the cumulant generating function. We look at this cumulant, and this is the center. This is the law of large numbers. It just takes a little bit more work to convert this into a proof. So we have k of theta and the average. So this is going to be the sum of k theta xi over n, and then I forgot to put the n with the theta instead of the x. But in the expansion, the n is going into the theta. So it's going to be summation theta over n, because theta has been replaced by theta over n. And then kappa 1 and theta squared over n squared times kappa 2 times theta squared over n cubed times kappa 3. Remember that these kappa 3s are now just for one random variable. So whatever they are just numbers. So now, because we have centered all the variables, kappa 1 is 0. So the first term is 0. Now the second term is the variance, and whatever it is, it's going to 0. Oh yeah, the thing is that there are n terms here. So the first term is theta over n times some constant, and we take n of those, so it will become theta. But fortunately that thing is 0, so the first term disappears. We have chosen things to make the first term disappear. Now the second term, it has an n squared in the denominator, and there are a total of n terms, and they are all the same. But even if they weren't the same, if they were varying a little bit, it wouldn't matter, as long as the kappa 2 is bounded, because there are n terms of those. So n theta squared times kappa 2 divided by n squared is going to be 1 over n order term. It's going to go to 0. So everything is going to 0 here. And that's what shows the law of large numbers. But this is not so pretty. The pretty part is the central limit theorem. Okay, now we get the beautiful property of the normal. Remember that the normal MGF is x of mu theta plus 1/2 theta squared sigma squared. So when I take the log, it is mu theta plus 1/2 theta squared sigma squared plus nothing. This is very important. So what does it mean? It means if you calculate the cumulants, the first derivative is mu plus theta squared plus theta sigma squared. The two, and when you differentiate theta squared, the 2 cancels and you get theta sigma squared. So when you set theta equal to 0, you get exactly mu. That proves that the first cumulant of this normal distribution is mu. What about the second? Well, now you have theta sigma squared. You differentiate that and you just get sigma squared. And there is no theta inside, so setting it equal to 0 doesn't do anything. And you get the second cumulant is sigma squared, exactly as I claimed. And all higher cumulants are 0, because theta has disappeared from the formula. And that's the unique feature of the normal distribution. That is what makes the normal distribution central. All higher order cumulants are 0. Any other distribution has non-zero third cumulant or fourth cumulant, and that's what makes them different from normal. So basically, tests for normality are based on testing kappa 3 and kappa 4. A large number of tests test, do you have a third cumulant? If you have a third cumulant, you're not normal. If you have a fourth cumulant, you're not normal. If both of those are 0, then you're normal. So that's a standard. The well-known test, kya naam hai uska? Jacques-Berra, exactly. Jacques-Berra tests for kappa 3 and kappa 4 being non-zero. So, and that's not the only one. There are many other tests like that. So this is the property, and now we will see why this is the central limit, because basically when you take the sums and divide by the square root of n, all cumulants from kappa 3 above will disappear. So automatically you will get normal distribution. That's the heart of the central limit theorem. So this is the calculation. K of theta 1 over root n. Now we are doing the same calculation. Now we are taking the cumulant of the sum divided by square root of n. So now we are doing the right scaling, the one that will not make the variance go to infinity and will not make the variance go to 0. It will stabilize the variance basically. So again, the square root of n can be merged with the theta. So I get that this is the summation theta divided by square root of n kappa 1. Now the kappa 1 has been scaled, so this term is going to be 0. Now the second term is perfectly balanced. You have theta squared over n divided by kappa 2. Kappa 2 is exactly the variance. So this is the sum of n terms. Each of them has 1 over n. So the summation will cancel with the 1 over n. So you will get theta squared times kappa 2. So this is theta squared times the variance. Now the third term has n terms. It's theta cubed kappa 3 and divided by n3 over 2. Square root of n raised cubed. So now you have n of those terms. That's going to give you an n factor in the numerator, but n3 over 2 in the denominator. So you will get 1 over square root of n in the denominator, which will drive this term to 0. All higher order terms will also be driven to 0. So basically you will get convergence to the cumulant generator function, which will be just theta squared times kappa 2. And that's exactly the normal cumulant. Remember what's the normal cumulant? It's mu theta, so mu will be 0, so it will be 0 plus 1/2 sigma squared. एक half missing है यहाँ पे. Oh yes, it's missing because I didn't put it in there. The formula is wrong. There should be a 2 next to the n, and theta cubed is going to be divided by 3 factorial. Not that it matters. I just forgot to put the 2. So the 2 is there, and then so this will be theta squared over 2 times kappa 2, which is exactly the the cumulant generating function of a normal variable with mean 0 and variance sigma squared. So here we have the central limit theorem, very simply, and nothing complicated about it. And that's the end of the slideshow and end of the lecture. So, okay, some people say that in some of my lectures I cover the whole course, and I think this is one of them like that. One could take about, and if we